everyone, my name is Suborno Isaac Berry from Berry Science Lab, and welcome to Probability Lecture 3. Today we'll be looking at conditional probability. So what is conditional probability? Well, let's start with a classic example. Let's say there were P people in a city. Of those P, exactly V of them are infected with some virus. So that means there were exactly P minus V healthy people. So eventually, scientists develop a test to check for whether you have such a disease. But they also send out a warning. This test has a false positive rate. So the false positive rate, he says, is P. Meanwhile, the false negative rate, he says, is N. One day, a man walks into the clinic to get himself tested for this virus. And the doctor eventually says that the test returned positive. He does have the virus. And the man freaks out, understandably. But then the man thinks for a second. He remembers this going on. There was a risk of a false positive reading. So he says, what if this is a false positive? What are the chances I'm actually sick? And that's exactly what we're going to solve for today. So, you might at first say, well, the false positive rate is P, so surely the true positive rate is something like 1 minus P. So the answer should be 1 minus P, right? Well, as you can see from a little bit of thinking, that's a really bad way to approach things. So how do we do this? Well, let's make a chart first. So there are going to be healthy people and sick people. And these rows are going to document how many came back negative and how many came back positive. So this is going to be the true negative square because it's for healthy people who actually were told that they were healthy. This is going to be the false positive square. Notice it's not the false negative square. For people who were told they were sick when they were actually healthy, this is going to be the false negative square for people who were told they were healthy even though they were actually sick. And this is going to be the true positive square for people who are sick and for whom the test came back correct or positive. So let's start with the false positive square. We know that the rate of false positives is P. So, logically, since there were P minus V healthy people, the percentage who got that false positive is going to be P. So, that means that there should be P times P minus V people in this section. And hence, since the total number of healthy people should be P minus V, that implies that this is just going to be P minus V minus this, which is 1 minus P times p minus v. Now, similarly, the rate of false negatives is n, so this is going to be n times p minus v. Meanwhile, the rate of true positives is going to be 1 minus n times p minus v. So now we know that this guy tested sick, which means that he tested positive. He's in one of these two categories. So, and remember, this is not ensured the actual number of people who are going to test this way. This is the expected value. So the total number of people who test positive are p times p minus v. Oh, wait. Oh, crud. This would be nv, because this is only infected. This would be p times p minus v plus 1 minus n times v. And the chances he's actually sick is the chance that he's in exclusively this lower right square, 1 minus n times v. And you'll notice that's not at all similar to 1 minus p. That is the message of conditional probability. Now, can we generalize this? Yes. That comes in what we call a Bayes formula. The probability of A given B has happened is equal to the probability of B given that A has happened multiplied by the probability of A divided by the probability of B. And the logic stems from this exact table logic. So, for instance, the probability that you were actually sick given that the test showed that you were sick is going to be the probability that the test showed you were sick given you were actually sick. Now, think about it for a second. Is it going to be 1 minus p? Well, just look at this table. The probability that you were sick, so you're one of the people, and you fall in the true positive range is going to be 1 minus n times v over v. It's going to be 1 minus n. Because, think about it. If you were actually sick, the probability that the test comes back positive is the same probability as 1 minus the chance that it comes out as a false negative. And the chance that it comes out as a false negative is n, which means that this is the chance of it coming out as a true positive. Think about it. So that means this is going to be 1 minus n. The chance of being sick in the first place is being one of the v sick out of p in total, and the chance of being one of the people who the test showed were sick comes from that p minus v plus 1 minus nv over p, which means these two cancel out, and we get the exact same formula that we did manually, but with a lot less effort. Now, there's also a valuable real-life lesson to be learned here. Let's say this scientist is advertising this test with only a 5% false positive and false negative rate. So you might say, well, that means it's going to be correct for a given person 95% of the time, right? You might even say, well, it's going to be 100 minus the rate of false positives minus the rate of false negatives. So it's going to be somewhere around 90, right? Well, what happens if we take, let's say, the total number of people is 1,000, the number of infected is 10. Plug those numbers in for a second. What do you get? The chance that it's correct, the chance that if the test comes back positive, that this guy is actually sick, given these conditions, and a 5% failure rate either way is what? Well, it's 0.95 times v over 0.05 times p minus v. So this is going to be 10 times 990 plus 1 minus n, 0.95 times v, which is 10. So now you will probably say, okay, so this is 19 over 20 times 10, 1 over 20 times 990, plus 19 over 20 times 10. So that's just equal to 19 over 2 divided by 99 over 2 plus 19 over 2. I actually haven't calculated this in my head yet. So this is 118 over 2, which is 59. And so 19 over 2 over 59 is going to be 19 over 118. Yes, that's the chance that if somebody is sick, and that's the chance that if the test comes back positive, that it's correct. 19 out of 118. That's not the failure rate, that's the correctness rate. Which means that it's literally much better to not trust the test, which gives you like a 90% or maybe 80% yield, than to trust the test. But that gets even more complicated in real life scenarios, because here we have two scenarios. You're either fully healthy or sick with one virus. In real life, we might have a test that checks if you're sick with virus 1, virus 2, or if you're fully healthy, or what strain of virus 1 you're infected with. In those situations, it's not as simple as, well, if it has such a low truth rate, then why don't we just always distrust what it says? In those cases, if you distrust what it says, like if it comes back saying V1, great. So you know you probably don't have V1. So, I mean, how do you choose between being healthy or having the different strain of V1? Exactly. That's why these false positive and false negative rates can be really misleading. I challenge you today to take those 10 and 1000 numbers. So this is 990. Oh, this is 10. Now, assume that the rate of false positives is equal to the rate of false negatives. So call them both x. Now, I challenge you to graph this. What do you find that's so unexpected? That's exactly the paradox of conditional probability.